Swayam Prabha. Digital India. Educated India.
Okay, we have been studying heat treatment, and that is one way of enhancing the strength of the material by getting the kind of phases that we want. So, we have certain alloying elements which have been added to the alloy, and then these alloying elements have to be organized in the form of different phases, and each phase has its own structure, and each phase has its own strength. And so, these phase transformations can be generated depending on the temperature of heating and the rate of cooling from that particular temperature. So, we have seen here that the hardness changes, the depth at which to which the hardening can take place changes depending on the alloy content. For instance, with higher alloying content you can have deeper hardening, meaning hardening can take place much better from this end to the other end. Whereas, if you have just surface hardening, then hardening will just take place over a very short distance from this rapidly cooled end. So, we have seen how martensite is formed. Martensite is basically a body centered tetragonal phase in steels. So, you have martensite start, martensite finish temperatures which are very important. Many times martensite start and finish temperatures are adjusted in such a way as to generate martensite as per requirement. For example, you need to generate, let us say, strain induced martensite. For example, so what happens is the martensite start is located just below the room temperature, and when you do mechanical working, then the mechanical energy that is given to the alloy results in formation of martensite, because martensite start moves upwards, moves above the room temperature as you give more strain energy to it. Sometimes what happens is martensite start is at room temperature or slightly higher than the room temperature, martensite finishes below the room temperature, and as you work the material, as the material continues to experience strain, the martensitic transformation moves towards completion, because martensite finish moves upwards and to higher temperatures. So, what I am saying is that the martensite start and finish temperatures are adjusted by chemical composition, and these temperatures enable us to generate strength at the time we want it to have strength. For example, you want the material to be a little softer while deformation, but you want it to be hard, or you want it to get hardened during service. So, that is what happens when you generate martensite at will. And so, the cooling rates, the martensitic start and finish temperatures play a significant role. Then you have tempered martensite, because martensite may be too hard, and then it might not generate enough impact toughness. So, to increase the impact toughness, you temper the martensite. So, what you get is a supersaturated solution of carbon in alpha ion. So, basically this is a slightly different structure as compared to the body centered tetragonal structure of martensite, and that is much harder. The tempered martensite is much softer, in the sense it has got much greater toughness. So, you lose some hardness, but you gain in terms of toughness. Now, we have seen salt baths as quenching media, and these salt baths are able to give us very uniform temperature distribution also, and lower the temperature of the salt bath and higher is the cooling rate, and cooling molten salt baths is only by convection, and agitation enhances the cooling rate significantly because convection heat transfer by convection becomes that much faster. So if you want to use salt baths for heating, then you need a different composition of salts, because here the melting point is very low. Where you have melting points, where melting point is very high, you need those salts which melt at high temperatures, and use a completely different salt bath composition for heating. Whereas for cooling, you can use the salt baths which melt at different temperatures, and cooling rate gets decided based on that. So you have effective cooling rates, temperatures, and then cooling rate in the range of 550 to 650 degrees centigrade. This is a special range because you have decomposition of the saltpeter, that is one of the so sodium nitrate will decompose, and then it will react with the iron. So that is why this 550 to 600 degrees centigrade is relatively risky range of temperature. So you have different cooling rates depending on the composition of the salt bath, and the cooling rates in this special range are given over here. The effectiveness of quenching media is we also discussed that. We have different quenching media, like water for example would give us a very high rate of cooling, whereas oil will give us a much lower rate of cooling. Then we saw cryogenic treatment, and then we came to heat treatment and defects due to heat treatment. Now many times what happens is during heat treatment the material gets overheated, either because of wrong setting of the temperature or due to wrong schedule of heating. So what we need to do is that the grain size which has got coarsened in the process will have to be brought back, in the sense you need to eliminate the consequences of overheating. So what we do is that we take corrective action in the form of normal annealing and normalizing. So you first anneal the material and then normalize it if it has been overheated and it has become highly coarse grained. For considerable overheating, apply double annealing or normalizing. So first annealing and normalizing at a temperature 100 to 150 degrees centigrade above the AC3 line, and second annealing at normal temperature. So basically it can be corrected by heat treatment itself. Burning on the other hand is oxidation of the grain boundaries. So we have seen that grain boundaries are regions of high energy, and in the presence of oxygen and high temperature, the oxygen attacks the grain boundaries preferentially, oxidizing the grain boundaries. So heating for long periods at high temperature in an oxidizing environment, under these conditions the boundaries get oxidized, and this creates this kind of material is rendered practically useless. So if you have carburization, or if you have let us say iron oxide formation as a result of burning, or you have regions enriched in carbon as a result of first stage of burning, then you need to have some corrective actions, like use homogenizing followed by double annealing, because now the carbon distribution has got disturbed. So you need to homogenize it followed by double annealing, as in case of overheating. Second stage is for the second stage where you have non-oxidized cavities, blowholes, etc. You can do forging, because you have cavities there which are not oxidized. If they are oxidized, forging will not help. So you have cavities which do not contain oxygen inside it, they are just cavities with nothing inside. So you can do the forging followed by annealing, because forging will close these these blowholes, etc. So these are typically situations when you are heating a cast billet and then you are trying to take it to further processing. So if you have a burning taking place, then you need to therefore use forging followed by annealing to close these blowholes. And the third stage is where iron oxide is formed, where the material has got really oxidized. Nothing can be done, it has to be remelted. So basically you have to take it for remelting, and no heat treatment can be used for as a remedy for it. So basically what it means is, if the boundaries, grain boundaries have got attacked by oxygen creating iron oxide, then you cannot correct it by any means other than remelting it. But if it has got not non-oxidized, if it is non-oxidized, then it is possible to handle the situation by heat treatments and so on. Oxidation, oxide scale due to oxidizing atmosphere. So then the best thing is to use a reducing atmosphere or a protective inert atmosphere, or you can have carburizing agents. So you can have gaseous agents like endogas, or you can have carburizing agents like cast iron chips, molten salt baths and things like that. Decarburization is something where carbon is lost from the surfaces, and therefore surface becomes devoid of carbon, loses strength, and then so the correction is in the form of machining off the decarburized layer, because you cannot bring the carbon back once it has got decarburized. You do not know how much carbon is, what is the depth of decarburization. So it is not that if you carburize it back it is going to help you. So the correction is that you just machine off the decarburized layer and take care of it. Okay. Well, decarburization can be prevented by heating in furnaces with reducing atmosphere. So basically it could be hydrogen, it could be either a neutral atmosphere also is okay. So endogas, hydrogen, these are all reducing gases. It could be cast iron chips or something like that. So this will prevent decarburization. But then if it has taken place already, if the decarburization has already taken place, then the correction is possible only by machining of the top surface, provided sufficient machining allowance is available. Then we come to another defect, which is excessive hardness of hot worked annealed steel, excessive hardness. So if there is excessive hardness, it means that the cooling rates have been excessive. So basically even when you might have annealed in a furnace or cooled in a furnace, the cooling rate was too much. Sometimes what happens is, in a highly alloyed material, the temperature time transformation diagram moves far to the right, as a result of which even a small cooling rate results in the formation of excessive amount of martensite, or resulting in excessive hardness. So the result is that we have very poor ductility, poor impact toughness. So if we want to retrieve the situation, then you need to repeat annealing, but then the cooling rate should be even slower. So the cooling rate should be slower. So one has to look at the temperature time transformation diagram for this. It is possible that the cooling rate was not set in consultation with that diagram, and therefore it was too much, even if it was annealed in the furnace. So then we have black fracture or free graphite present, okay, which occurs as inclusion in the steel. So this is again due to excessive heating time, slow cooling and very slow cooling after annealing. Basically the free carbon generation or black fracture or presence of graphite, etc., is the outcome of too much of time being available for diffusion. So you have high temperature and you have large amount of time available, and that is how diffusion is facilitated. So it is important to heat the steel to a high temperature and forge it thoroughly. So basically what you are trying to do is, by forging the material, you are not allowing the just the diffusion to take care of uniform distribution of carbon. You are physically mixing material. If you forge the material, it means that you are deforming the material, you are mixing the different regions of inhomogeneous carbon content together, as a result of which the homogenization or uniform composition takes place, plus the strain energy that is imparted in forging aids dissolution of any carbon or any graphite that might have been generated as a result of this diffusion process. So heating the steel to a high temperature and for thorough forging is a good idea if you have a graphite type of situation arising. You have quench cracks, again this is because of various reasons. Now if they are at the grain boundaries, then one has to check whether there is segregation of tramp elements or certain elements like boron, if they have been added for strength, whether they have segregated to the grain boundaries, due to which you can have quench cracks being generated at the grain boundaries, plus there can be internal stresses due to volume changes. You see that you have a big workpiece, as seen in the previous continuous cooling transformation diagrams. You have at the surface the maximum cooling rate, in the interior the cooling rate is much lower. So the microstructure at the surface and microstructure in the interior are can be different. Assuming that the microstructure at the surface and the interior are the same, still they do not occur simultaneously. So the outside microstructure results initially in the in expansion, volume expansion. Then at that time the interior microstructure has not transformed because the cooling rate is much lower. Then by the time the external microstructure or external structure comprising of martensite starts shrinking, the cooling in the interior of the part results in formation of martensite, which means the interior is now expanding. In the interior portion, the transformation from austenite to martensite leads to a volume increase, due to which the interior expands, the exterior layers tend to shrink, and so this results in excessive amount of strain at the surface. And martensite, by virtue of its relatively low fracture toughness, would result in quenching cracks being generated, and the grain boundaries being the ones where most of the cracking would take place, because this is a region of large amount of disorder. So now this defect cannot be corrected, because once the material has disintegrated, you cannot do anything about it. Once the cracks have formed, you cannot do. So to avoid this, you can have some steps, you can have some measures taken to avoid, by avoiding sharp projections or sharp notches or sharp changes in cross section, so abrupt changes in cross section, right. Then the residual stresses which are present from the previous processing should be annealed and relieved, because the stresses which are generated during this process will get added to the previous residual stresses and finally cause early failure. So it is important to have some design considerations, design for heat treatment type of thing, where you avoid sharp corners, you avoid sharp transitions or very abrupt transitions, heavy transitions from very thick to very thin. So the transition being abrupt is one thing, large transitions from a diameter of, let us say, 50 mm to 1 mm. So this is a very large transition, 100 mm to say 10 mm, large transition. So these large transitions have to be avoided, so that the cooling rates are more uniform, the microstructural changes are more uniform. And then heating to excessively high temperatures, because the stresses which are generated are proportional to the extent of cooling, because you see if you cool from a very high temperature, delta T is large, and therefore Cp delta T, alpha delta T, not Cp delta T, alpha delta T is something that is much higher So, the extent of thermal expansion and extent of thermal contraction would be much more if you have heated to a very high temperature. So, the extent of thermal contraction from a high temperature would be very high, and so it is important to heat the material to as low a temperature as possible for the change to take microstructural change to take place. So, you must look at the temperature that is just sufficient. I mean, excessive heating does not really help, as it creates stresses, excessive more stresses on the exterior. Cooling slowly in the martensitic range is important, because if you cool fast when the martensite has already formed on exterior, if the cooling rate is not reduced, then there is a chance that the transformation in the interior will take place very rapidly, and then it will result in cracking. Similarly, the cooling rates, if they are really fast, they can also do the damage on the surface itself by excessive rate of shrinkage. So, on one hand there is thermal shrinkage countered by the tendency to expand, okay, on the part of the metallurgical transformation. So, that is why there should be an interrupted quenching. There should be an interrupted quenching, meaning that during the martensitic transformation range, you that is after the martensite start, or maybe just above up to martensite start, you can quench fast, then reduce the cooling rate very to a very slow rate, so that the transformation takes place at a very slow rate, and stresses are reduced. So, this can be achieved either by let us say reducing the cooling rate, meaning having the cooling medium at relatively high temperature, or by quenching in oil, or giving treatments like Marr tempering, for instance. So, Aus tempering, Marr tempering, these are some of the treatments which can be given, and the usual practice is to temper the martensite immediately after quenching, so that you do not generate cracks even after the quenching has taken place. That is because, you see, after the quenching has taken place, immediately after quenching you may not see any cracks, but with time these stresses which have been set up on the surface may get relieved, and this relief can take place by formation of cracks. Okay. So, that is the reason why it is important to temper immediately after quenching, so that the fracture toughness of is introduced. The fracture toughness gets introduced into the material, so that no cracking takes place thereafter. In fact, brittleness is an outcome of quenching of martensite generation, and if you do not temper it, the product will tend to behave brittle. Although it may be hard, it might not have cracked, but still it will be brittle on the surface. So, a small impact can generate these cracks and render it useless. So, it is important to immediately temper it after quenching. Now, many times what happens is, when we are heat treating tools, particularly you have made a tool with a specific geometry, and you want to harden it, you want its strength to increase, and you want as much martensite as possible to be generated. Now, in this whole process of volume change, the dimensions also get altered, because when the volume change takes place, naturally the cavities become smaller. For example, you have machined a die or something with a certain hole diameter. Now, after the heat treatment, and hole diameter will tend to become smaller than what it should be, because the volume expansion due to martensitic transformation will make it smaller. So, it is important that the deformation and volume changes after hardening have to be taken into account during designing the workpiece itself, because supposing you want a diameter of 50 millimeters, and then by virtue of this martensitic transformation expansion of volumetric expansion, you end up with a diameter of 48 millimeters. You want a diameter of 50 millimeters. After martensitic transformation, it ends up at 48 millimeters. Then getting it back to 50 millimeters will mean that you will have to machine off those 2 millimeters of extremely hard material, and that is something that is extremely expensive, meaning extremely difficult to do. So, that is why one has to therefore provide some allowance. Let us say you make the diameter of say 51 millimeter, and after the martensitic transformation it may come down to, let us say 50 millimeters or thereabouts, and then a small machine cut might be required, so that you have a uniformity in the removal of material, meaning that when the material gets distorted during heat treatment, the circularity might get disturbed. So, the form errors might get introduced. So, in order to eliminate those form errors, you might need a very small cut to be taken, and that should be enough to get the diameter, the desired diameter back. So, what I am saying is that significant volumetric changes or significant deviations from the dimensions can be avoided by providing certain allowance. These allowances are standardized for every composition of steel, and therefore one has to stick to the cooling rates, for example, which are recommended, and the heating to a specific temperature has to be adhered to, so that the volumetric changes are controlled, and whatever allowances you might have given to the dies or to the tools will result in minimal distortion or minimal deformation with respect to the desired shape that you had wanted. So, this is a very important thing. So, you need alloy steels which are slightly deformed by quenching, and such alloy steels are designed by chemical composition. For example, D2 is a composition of alloy steel which is used for cold working tool steels. So, here the volumetric changes or the dimensional changes due to heat treatment are extremely small, practically nil. So, you do not need to you do not need to provide some allowances for these for the heat treatment and so on. So, basically that is important. Another issue is of corrosion, pitting or groove type of destruction of the surface of an article, and typically it happens when you heat in molten salt baths, because if the salt starts reacting with the surface, if the workpiece and salt react, then it will attack the grain boundaries or regions which are relatively high in energy. So, high content of sulfuric salts or is something that is that would result in this, or the bath is enriched with oxygen, due to which iron oxides get formed, and then there is pitting, or when I say it is not exactly corrosion, but it could be oxidation as well. So, we and then decomposition of the salt, as we saw that chili saltpeter gets decomposed at a certain temperature. So, then you need to make sure that the salts which you have added are suitable, or they do not decompose at the temperature of heat treatment. So, controlling the salt composition is therefore very important. Deoxidation of the bath is important. One of the key USPs is that the environment in the salt bath is not really oxidizing. So, but then oxygen can still get into the salt bath. So, you need to keep deoxidizing the salt bath and eliminate the oxidizing atmosphere when heating in the flame furnaces. So, you should have a carburizing flame. For example, we know that when we use oxyacetylene type of flame for heating, you can have oxidizing flame, carburizing flame, or a neutral flame. So, you need a carburizing flame for basically reducing atmosphere at least, so that you do not have this corrosion. In fact, corrosion can take place due to different reasons, meaning apart from oxygen there could be many other things like sulfuric salts, for example, due to which sulfur can react with steel for forming iron sulfides. So basically we do not want the surface of the steel to get attacked by these salts. Okay. Now, so deformation in hardening may be substantially reduced by employing special heat treatment procedures which enable tempered martensite and an increased amount of retained austenite to be obtained after hardening. So, this is achieved by increasing the hardening temperature to a certain extent and by slow cooling to be to the temperature range of martensitic transformation. So, this is what we have seen in this slide, and this applies to all heating media. Warping is another kind of deformation. Now, warping is something where deformation takes place, a different amount of deformation takes place with respect to location, due to which, let us say you have that rotation of the or the let us say twisting at one point you have say 2 degrees, at another point it is 3 degrees, third point it is 4 degrees. So, this is how you find that there is warping which has taken place, that is asymmetric deformation of the article in quenching. So, the change in shape is not symmetric, the change in shape is asymmetric, and due to which you find the article in a warped condition. So, this is again non-uniform heating or cooling, or in fact if there are large changes in cross section also this can happen. For example, you have volume you have different very different cooling rates in two different regions, right. Now, if you have different cooling rates, then you can have different volume changes taking place, different degrees of volume changes taking place, right. And so, when different volume changes take place in different regions, then this will result in different degrees of deformation, due to which you will have warping taking place. So, that is what we mean by volume changes in cooling or in heating. Non-uniform heating or cooling also is can be the case. Again, when you have very large cross sectional changes, or when you have a part which is highly asymmetric in nature, due to which you have non-uniform heating and cooling taking place. So, many of these result in non-uniform transformations, non-uniform volume changes, which in turn result in non-uniform strains being experienced, right. And then from point to point you have different magnitudes of deformation, which finally on a macroscopic scale is seen as warping. And then if you are doing quenching, a quenching operation where the article is not immersed into the bath in the right position, in an inclined position, meaning that the entire article does not see the same bath temperature. For example, if it is in an inclined position, for example, then the bottom of the article gets quenched first, and then the top of the article is not going to see the same quenching bath temperature as the bottom had seen. Therefore, now one portion of the article sees one cooling rate, other portion sees another cooling rate, the volume changes are different, as a result of which again you have warping taking place. So, that is the reason why we need to avoid these by taking certain steps. So, one thing could be just heat uniformly for hardening. So, there are means of heating uniformly. There are standard equations or standard guidelines about what should be the spacing between two billets or two articles when they are being heated in the furnace, so that the heating medium is available to each article to heat it uniformly, or as well as to place it in the furnace for sufficiently long time. So, the heating time, heating rate all these parameters have to be set so that heating uniformity in heating is facilitated. So, for instance, if the alloy steel has got low conductivity, obviously alloy steel will have low conductivity, then the heating rate has to be small and the heating time has to be large, so that the heat is uniformly distributed over the entire volume. So, it is important that we heat uniformly following the guidelines of heating, rather than try to maximize the volume of heated material at the expense of quality of heating. Another thing is, supposing you have these volume changes and then warping has already taken place, then you need to avoid this, you need to anneal, normalize or temper at a high temperature before hardening. What it means is that you need to hold it basically at a certain temperature and then cool it down to harden it. So, here what happens is the transformation is not going to take place to martensite entirely. It will get transformed to say perlite or some such phases, and then the remaining austenite will get transformed to martensite. So, what we are doing here is we are minimizing the strains which are caused by volume changes, as well as so the differential changes in the in volume in different regions of the article are therefore avoided here, and then quench as uniformly as possible in hardening. So, again the just as we said, the heating should be uniform, the quenching also has to be at a uniform rate, and this becomes a little complicated because if, particularly in case of parts having large cross sectional changes, there maintaining a uniform quenching rate becomes a little difficult, because wherever the cross section is thin, the quenching rate or the will be much faster. The quenching rate as felt by the material will be faster as compared to the quenching rate where the cross sections are relatively big. So, it is important that we design the quenching process to be as uniform as possible, so that we get uniform hardening. Hold the article in the proper position when lowering it into the quenching bath. So, again this is for uniform heating of the or uniform quenching. Use special quenching jigs. The defect may be corrected by straightening or grinding of the. Now, many times to avoid warp, you know that the things are going to warp, I mean the article is going to warp. So, what you do is you fix it, because if you quench it freely, you are allowing a free change in shape to take place. On the other hand, if you fixture it properly, then what you do is you force it to be in the final shape, into the desired shape when it is being quenched. So, effectively what is happening is you counter the change in shape due to the volumetric change that is taking place. So, now care has to be taken in that the volumetric change should not result in introduction of too much of stress or too much of residual stress in the material, so as otherwise it can result in cracking. So, it should have a small amount, I mean the restriction provided by the jigs should be a little small or to a reasonable extent, so that no cracking takes place. So, this defect is corrected by straightening or grinding if the grinding allowance is sufficient. So, basically what it means is that you have a part that is warped, but so you extract from the mass of warped metal the geometry of the part you really want. So, that is why it means you need to provide for a lot of extra material, so that even after warping you can machine off the extra material and extract out the part which is of the shape and size which you had wanted. but then this leads to loss of material. So, basically the design of the heat treatment should be such that the jigs restrict the extent of warpage. They may not be able to restrict it completely, some warpage might have to be allowed, otherwise if the jigs are too firm, then they might result in cracking. So, that is why the jigs have to be a little cannot be too firm, meaning they need to permit some amount of warpage, but then they restrict the warpage, and then small amount of defect. So, the basic idea is to minimize the extra material that needs to be provided. I mean, if you have a very free warpage taking place, then you need much more extra material to extract out the part you need to the dimensions you wanted. This is another issue of insufficient hardness after quenching and soft spots which are generated after quenching. So, this is basically loss of hardening in spite of the fact that it is alloy steel, you have heated to a high temperature and you have cooled it at a higher rate. One possibility is that in trying to minimize the temperature from which it is cooled down, because earlier we have seen that to minimize the stresses you should use as low a temperature as possible to heat treat the material. But now if you overdo that, then the temperature might be too low, you might be quenching from too low a temperature, and therefore you might not get sufficient hardness. So, this is a very important aspect. So, the lowest temperature is governed by the sufficient hardness that you get, highest temperature is governed by the possibility of grain coarsening, burning and things like that. So, basically consequences of overheating as well as excessive stresses being introduced due to large temperatures being used. So, these are the two temperature limits. Even if you do not overheat to the extent of grain coarsening and burning, even if the hardening temperature is too high and you quench from there, the you will get lot of stresses. So, that defines your highest temperature of hardening. Insufficient hardening, the risk of hardening it insufficiently defines the lowest temperature of hardening. So, basically your hardening temperature or heating, to what temperature should you heat the sample to? It should be between these two limits, one defined by insufficient hardness, other defined by excessive stresses being generated during quenching. So, you have holding time also, which is very important at these at the hardening temperature, because you need equalization of temperature everywhere, and so you get, if you want through hardening, then it is very important that right up to the center of the part of the article, the temperature has to be homogeneous, and cooling rate is too slow is another problem. So, if you have a combination of too low a temperature and too low a cooling rate, you will have extremely poor hardening taking place. So, that is why so this insufficient hardness after quenching can be corrected by increasing the cooling rate and increasing the temperature to which it has been it has to be hardened. Every steel has got its own specification of temperature to which it should get heated to, and the rate of cooling, the quenching medium, the extent of agitation which will result in a specific cooling rate. Everything is defined by the manufacturer of these tool steels these days, so that the user is not left experimenting with different cross sections and different specimens to get the kind of microstructure one wants or get the properties one wants, right. Now, here there is another variety of loss of hardness. It is because of soft spots. So, it is not that temperature was wrong or the cooling rate was less in general, but then you had soft spots, meaning local cooling rates were not good enough. That is because of vapor accumulating, that is due to formation of bubbles very close to close to the surface of the article being quenched. So, what happens is, as you quench the article, the quenchant evaporates immediately, and then the bubbles which do not leave the quenchant, they cover the entire surface and they reduce the heat transfer rate there. So, wherever bubbles are formed, essentially the thermal conductivity of the bubbles being very low, you have a relatively low quenching rate there. So, as a result, you create the soft spot in the region where the bubble was formed, right. So, this is one aspect. Other aspect is, you can have localized decarburization. Many times the water vapor or presence of oxygen itself, dissolved oxygen. So, these are all things which result in reaction of surface carbon with oxygen due to local decarburization at the surface. And then third reason could be inhomogeneity of initial structure in the solidification of steel itself, meaning that you do not have uniform distribution of carbon. Now, so this basically can be corrected by homogenization, or you can heat the structure to a sufficiently high temperature, maybe to austenitic temperature or so, a single phase temperature where the diffusivity of carbon is relatively high, and then you have a uniform distribution of carbon, due to which you have a good possibility of getting uniform hardness, assuming that the other two, that is vapor accumulation etc., soft spots are not generated because of bubbles being created. So, this inhomogeneity is because of composition, chemical composition, due to the initial structure and solidification of steel. We have seen that as the solidification takes place, the carbon continues to get rejected into the solution. So, the initial solidified material has relatively low carbon, and the subsequent solidified material has got relatively higher amount of carbon. So, there is a gradient of carbon during solidification itself, and so unless you homogenize the material, it is not going to be possible to have uniform carbon everywhere. So, soft spots can be generated for two reasons. One is that the cooling rates are not sufficient or not equal, and certainly not sufficient in the vicinity of where the soft spot was generated, and the chemical composition, meaning the carbon was not adequate in the region where soft spot was generated. So, we can use the a few methods to correct the defect, where you have a quenching medium where which does not evaporate at the temperature and does not generate the bubbles, and these bubbles can be removed by agitating the quenching medium. So, you can remove, if you have a static quenching medium into which you immerse the high temperature article or high temperature workpiece, then you will have bubble formation and bubbles will stay there and affect the cooling rate. But on the other hand, if you are continuously agitating the quenching bath, then due to that agitation, not only that the heat transfer rate increases, but also the potential for forming these bubbles is minimized. Now, if you are quenching in a salt bath type of furnace, then these bubble formation can be avoided completely. So, it is a very effective quenching medium. In fact, salt bath therefore gives you very good quality of quenched product. So, you have more homogeneous structure by annealing, and so annealing and normalization basically are things again which lead to homogenization. So, localized decarburization will get addressed by this, and during heating itself you can prevent decarburization. So, localized decarburization can be prevented by heating as well as using an atmosphere which is congenial for that, meaning it is a carburizing atmosphere or reducing atmosphere that should be utilized. Excessive hardness after tempering is a problem, meaning the tempering process has not been done. So, either you are tempering at a relatively low temperature or not allowing enough time. So, the driving force for diffusion which results in tempering is temperature and time. So, you have temperature and time both needed for diffusion to take place and therefore tempering of martensite to take place. So, it is important that the sufficient temperatures are reached, and therefore, if you already have a problem of excessive hardness after tempering, temper it again with proper temperature and holding time. So, you need to give it opportunity to diffuse, carbon to diffuse out of the martensite, right. Insufficient hardness after tempering. So, earlier case it was excessive hardness, now there is insufficient hardness. Now, you have tempering temperature that was too high, which means that the driving force for diffusion of carbon out of the martensite was too high, and therefore, you need to harden it again by annealing and rehardening. So, you first anneal it to minimize the stresses. So, because in the next hardening step, these stresses should not result in cracking. So, the previous defect which we saw. So, you first anneal the material and then reharden and then temper it at the correct temperature. So, here if you have employed the wrong temperature for tempering, then you have to go through a big process of annealing first, rehardening and tempering at the normal temperature. So, it is very important that certain defects are better avoided, because correction means a very long procedure which is extremely energy intensive and expenditure intensive. Another defect could be erosion, that is reduction in size of the article or distortion to its form due to loss of metal from its surface. So, actually many times what happens is these metals form oxides which are volatile in nature, right. So, these volatile oxides can evaporate and then continuously material can be lost from the surface, that is one. Another way is, another possibility is that particularly in salt bath type of situation, the chemical reaction between the salts of the salt bath or oxidation of the metals can result in rapid removal of the material, because now the material that has reacted with the salt bath or the quenching medium will get removed due to agitation, and therefore, you will have shrinkage. So, you put 1 kilo of article, by the time you have heat treated it, you get half a kilo of article. So, half of the kilo is gone as dissolution in the salt bath or the quenching medium. So, we need to therefore deoxidize the salt bath with borax or so this borax will form boron oxide of boron, and then ferrosilicon will also remove the oxygen. So, ferrosilicon, because silicon is the one that will react and then remove oxygen from, so the salt bath will get deoxidized. And the second thing is you properly position the article in reference to the electrodes of the electrical salt bath. So, that is another issue where the material removal can take place, particularly if the surface becomes too anodic with respect to I mean it becomes anodic, it will tend to start dissolving and the shrinkage will result. Now, we need hardening not throughout the workpiece, but we need surface hardening. So, we need what we call as increase of hardness at the surface, and which is achieved by change of the chemical composition on the surface by, let us say, carburizing. Carburizing means you increase the carbon content on the surface, and this carbon content on the surface results in the martensite formation only on the surface. Why? Because if you heat it to an austenitizing temperature, the high carbon austenite will be on the surface, the relatively low carbon austenite will be in the interior, and then you quench rapidly from this a single phase to the final phase that you want, that is the martensite on the surface. Interior might have much less carbon, due to which it might not form martensite, or it might form relatively low carbon martensite. So, the lattice distortions would be very low, but then the hardness at the surface would be very high because the carburizing took place at a very rapid rate of cooling, and so the martensite formation took place at a rapid rate of cooling, and therefore you have higher hardness at the surface. Interior, if you have relatively low carbon, then the volume changes are also relatively low, and therefore the stresses which are introduced in the carburized hardened layer are much smaller. So, if you have a relatively low carbon interior and a high carbon exterior by virtue of carburizing, then you are less likely to introduce cracks on the surface. Cyaniding involves increase in carbon and nitrogen content on the surface, basically to form carbides and nitrides. So, it is important that the chemical composition should have carbide formers as well as nitride formers. So, you have carbide formers in the form of iron, you have tungsten, you have molybdenum. So, these are carbide formers which have got very high affinity for carbon, and nitrides are formed by say aluminum, for instance, then titanium nitride. So, these are there are certain elements which form nitrides. So, if you want to cyanide the material, some of these alloying elements should be present, so that they form relatively hard phases and then the surface can get hardened. Similarly, you have what is called as carbonitriding, where you have hardening of surface by diffusion of carbon and nitrogen into the surface. So, the difference between carburizing and carbonitriding is that carburizing refers to increase in the carbon content by let us say putting let us say having it in by having cast iron pieces around the workpiece and so on, or you having a carburizing environment itself. So, the composition of the gas around it generates the carburizing environment. So, here you have carbon diffusing into the top surface and forming austenite here. Carbonitriding, hardening of the surface by diffusing carbon and nitrogen both into the surface. So, that is the difference, and you have carbon diffusing into it, forming interstitial carbon. So, this is when you say diffusing carbon, it means it has to go into the interstitial, right. Now, here the carbon content would in the surface layer might result in increase in the cementite also. So, you want you can increase the cementite content on the surface as well as the martensite content on the surface. So, here you have diffusing carbon and nitrogen occupying interstitial locations on the in the lattice, so that you get carbonitriding, meaning little harder surface condition at the surface. And then here nitriding means only diffusing nitrogen into the surface. So, you have nitrogen going in there, and if you have nitride formers like aluminum, titanium and so on, you will have nitride formers formation as well. Flame and induction hardening is something where you have I2R heating due to eddy currents introduced into the by induction heating. So, induction hardening is a very commonly used method for most of the surface hardening processes, because you can control the skin depth, as it is called. So, the eddy currents do not circulate over the entire cross section, they circulate up to a certain depth on the surface. So, depending on what is the depth of the surface you want to be carburized or to be heated, you can have these electrical parameters which are set, that is voltage and the current. So, that the current induced is also controlled. So, you have I2R heating or eddy current heating on the surface up to a certain depth, okay. And then when you quench that that part, then you have a very high hardness on the surface. So you don't need to increase the chemical composition. So what you are doing here is that you are increasing the temperature from which you quench selectively. So you have selectively increased the temperature of the surface to a higher value, and then you quench from there, and therefore you have a heat treated layer equal to the skin depth of few millimeters through which these eddy currents are circulating. Instead of electrical means, you can have flame hardening also. So you can heat up the surface to a high temperature using a flame, and then you can harden that as well. But then care has to be taken that the flame should be either neutral or preferably reducing flame. It should not be oxidizing flame at all. Now coming to heat treatment of light alloys, we have a number of light alloys like titanium, yttrium, barium, scandium, aluminum, strontium. So these are all materials which have got extremely small density, very low density, right. So you have titanium having 4.5 gram per cc, yttrium 4.47. So lithium is very low, and that is the reason why we have aluminum lithium as a very popular material in aerospace industry. Sodium potassium is used in various applications, but not in the aerospace industry in spite of having a low density because of their higher reactivity. But then you have materials like aluminum and titanium being used in aerospace industry very strongly or very commonly. You have cesium and some of these additions like magnesium, cesium, these are used very extensively in the aerospace industry. And most of the times these aerospace technologies come to automotive industry also, and then for premium grade vehicles, for lightweighting, or even premium grade electronic goods like mobile frames or laptop frames, you use lightweight materials. So people advertise laptops of very low weight. So that's where the magnesium content or aluminum content is much higher. So you have different light alloys, and these each one of these has its own properties, and so the heat treatment and the environment in which the heat treatment is performed will vary depending upon the chemical nature and its reactivity with different atmospheres that are used for the heat treatments. Now you see that the alloys have certain amount of density, the light alloys, and then the Young's modulus, the ratio of different criteria based on which this one can compare these alloys have been given here. So this is from Ashby, Professor Ashby's work from Cambridge, and so here you have the this ratios. These are used as standard tables, or these are used as very standard pieces of literature for selection of materials. And so light alloys are selected based on different ratios which are dictated by the application. And so with this we will stop here and continue with the heat treatment of alloys in the next class, of light alloys in the next class. Yeah, heat treatment of light alloys. Yes.